So we're going to take a look at velocity and acceleration and projectile motion. And all three of these concepts have to do with vector value functions. So it's great application. So as an object moves along a curve in the plane, that would be 2D, the coordinates x and y and its center of mass are each functions of time t. And I'm sick of using the letters f and g to represent the two functions, those components. So I'm going to use x of t and y of t instead. So the vector valued function, which we also can refer to as a position vector, if we're using it to model motion, will be x of ti, y of tj. So from this, so this is your position function. And you're in, some bug or fly is flying around or whatever. What's the velocity, acceleration, and speed? So let's do the definitions. Velocity, which a lot of times is denoted v of t, it's still a vector valued function. Okay, so if you're going to handwrite it, please put little vector hats on top of these. Okay, especially on your handwritten work. And that's the same as r prime, the position function's derivative. And that'll simply be a vector valued function where the components are the derivatives of the position vectors derivatives. Acceleration, a of t, r double prime. So you're going to have x double prime of t and y double prime of t be the components. And finally, speed. A lot of people think velocity and speed mean the same thing. Be careful. Be very careful. It's not. Speed is a scalar. Speed is the magnitude of the velocity vector. So please know that. So you're going to have square root of the sum of the squares of the components of the velocity vector there. Okay, now in 3D, definitions are similar. So this is just all for 3D. You got your motion, your position, vector valued function, x of t, y of t, z of t are the components. Velocity vector is a vector valued function with the derivatives as components. Acceleration, another vector valued function with the second derivatives for components. And speed, which is the magnitude of the velocity vector, which is going to be equal to, fill in the blanks here, big old square root, x prime of t squared plus y prime of t squared plus z prime of t squared. Goes underneath the radical. Yeah. It's considered a scalar function, not a vector function. The speed is a scalar function. Okay, let's do an example, and then we'll do a lot more examples. So let's say you're simulating motion in the plane, so in 2D, and let's say your plane curve C is described by this vector valued function with components 2 sine t over 2 and 2 cos t over 2. Sketch the graph. Well, you can go on your graphing calculator like we did last time, because this is a 2D vector valued function. And since you are graphing trig, make sure you're in radians mode. If you graph this, please make sure you indicate an orientation, because this particular curve is a circle centered at the origin of radius 2, and it's moving clockwise. So make sure you put one arrow here that denotes the orientation. Great. I'm done with letter A. I sketched the graph. Now let's give both the velocity and acceleration vectors. No problem. So v of t, v stands for velocity, which is exactly equivalent to r prime. And we're going to start the brackets here because we're going to do component form. When I take the derivative of 2 sine t over 2, 2 is a multiple. And when I take the derivative of sine, I'm going to get cos t over 2. But using the chain rule, I have to multiply that by the derivative of t over 2, which is 1/2. So I can reduce this to lowest terms, so the 2's cancel. And similarly, for cos, the derivative of cos is negative sine. So you're going to have a negative 2. You're also going to have a half factor in there, sine t over 2. And to make this look a little prettier, after we do the reducing, let's do cos t over 2 for the first component, and negative sine t over 2 for the y component. Okay, so that's velocity. What about acceleration? Well, of course, I don't have enough room. So let's do acceleration. We can call it a of t, but that's exactly the same as r double prime. And that's going to be the derivative of the velocity vectors component. So the derivative of cos t over 2 using a chain rule is -1/2 sine t over 2. And then the derivative of negative sine t over 2 is -1/2 cos t over 2. And we're done with letter A. Now for letter C, this is a special question. You have to be careful that you don't think this is always true for every vector valued function, because some students, they see one example and they think it's pertinent for everything universally. And that's a dangerous thing to believe. But here, the speed for this particular motion is always a constant. In other words, circular motion leads to constant speeds. Does that mean every single vector valued function is going to have speed that's a pure constant? No. Usually speed is a function of t. Okay. But for this particular one, it's going to turn out kind of cool, where the speed is always going to be a pure number. So let's do speed here. So speed is the magnitude of velocity. And we already got our velocity vector here in part B. So you're going to go square root of the sum of the squares of the components. Okay. So okay. Now, when you square a negative, of course, you get a positive. So the first term here under the radical is cos squared t over 2. And the other component is going to be sine squared t over 2. Does anybody know a special trig identity that says, cos squared plus sine squared is equal to nice number?
1.
Yeah. So we got square root of 1, but that's just 1. Aha. So it turns out that this particular motion gives speed as a constant. Does that always happen? No. Do not think this is always going to be the case. That's dangerous. But for this one, yeah. And then the second part of the question, it kind of got blocked out there, is what is true about the relationship between velocity and acceleration when speed is a constant? So it gives us a hint. Look at their dot product results. So let's take the dot product of velocity and acceleration. We're going to use our answers here from part B. So taking the x component here, so I got cosine t over 2 times the x component for acceleration was -1/2 sine t over 2, and then plus, and then multiplying the y component for velocity, that was a negative sine t over 2. And I'm going to multiply that by the acceleration's y component, that was -1/2 cos t over 2. Okay, let's do some cleanup here. What do you think about this sum here? If I put the coefficients in front of the trig functions, maybe you'll be able to see a little better what's going on. A negative times a negative is really a positive. So this second term, but I still bring the coefficient of 1/2 out in front. What do you think, guys? What is this sum going to end up being?
0.
And what is true? So basically we're saying that the dot product of velocity and acceleration is 0. What does that say about their relationship if you were to graph them?
They're orthogonal.
Very good. Yeah, they're orthogonal. You know, V would be going in one direction, but A would be exactly 90 degrees with it, right? So they are orthogonal. And that's the answer. Is that always the case? No, but it is for this particular kind of motion. Sometimes you get lucky and velocity and acceleration are orthogonal to each other, maybe even briefly or something while the object is moving. And we're done with this example. circular motion. Okay, example 10. Example 10 is going to be done in a physics class, guaranteed. I had a student some years ago who took me for Calc 3, and then I think he took his physics 2 or 3 years later, so he forgot some of the Calc 3. And he came to my office hours one time and said, "Hey, I'm doing a physics class. Can you help me?" I said, "Sure." You know, I don't know a whole lot about physics because I don't remember a lot. So we were looking at the problem, and it was exactly this problem, essentially. And he goes, "Oh, yeah, now I remember." So graphing t squared minus 4t. So if you go to your graphing calculator, you can graph this because it is a two-dimensional vector value curve, and just make sure you're in parametric mode on your graphing calculator. And so your x component is t squared minus 4, and your y component is t. Now be careful when you do graph vector valued functions, because you want to make sure that your range is correct so that you can see the whole picture. So if I enter in t squared minus 4 for the x component and t, now I'm just going to hit graph. Let's see what happens. I claim that that's not the whole picture, and you got to be real careful. If I go to window, the reason why is because my t minimum was 0 and my t max was 10. Better, I should have a t minimum that's negative. So I'm going to have my t minimum be negative 10 seconds instead, and I'll leave my t max as positive 10 seconds. Now, whoo, there's the whole picture. It's a horizontal parabola opening up to the right. Looks like the vertex there is on the x-axis at the 4. And so if I graph this, show the orientation there with an arrow. Okay, so we sketched the path of our object. So our object is moving along this parabola. You know, maybe it's a little bug walking there. So we're going to find the velocity and acceleration vectors at 2 locations. Once when time t equals 0 seconds, and the second time when t equals 2 seconds. And we're even going to sketch both velocity and acceleration at those times. So we'll do t equals 0 seconds first. Now, before I even get velocity and acceleration, let's start with step 1. Let's get the position. I want to get the position of our little bug at time t equals 0 seconds. Well, how you get your position? Well, you plug 0 seconds into your position function, which is the original vector valued function. So you're going to go, what's r of 0? So everywhere you see the t, the parameter, you substitute 0, and I get the location negative 4, 0, which is right here. That's where the tip of the vector would be. So the point negative 4, 0 is where the bug is located at 0 seconds. That's location. Fine. Step 2, let's get velocity. Let's get the velocity vector, okay? So v of t, which can also be denoted r prime, they're the same guy. It's a vector valued function, so put in those angular brackets, get ready, and go ahead and take the derivative of the components of your position function. So the derivative of t squared minus 4 is 2t, and the derivative of t is 1. Boom, there's our velocity vector. Yeah, fantastic. The next step, you could call it step 3. I'll just say I'm still in step 2. I want to find out what the velocity vector is exactly when time t is 0 seconds. So just substitute. And I get the vector 0, 1. Okay. Now let's graph the vector 0, 1. You got to be careful. In standard position, the vector 0, 1 would be located where? Well, first I would find the point 0, 1, which I believe is on the y-axis. And then I would draw a vector starting at the origin where its tip ends up at the point 0, 1. Now, this is not where I want the vector on my graph. What I need to do is I need to translate this cute little vector that's pointing up and move it to the point where it's associated with, which is on my curve here at the point negative 4 So there's the velocity vector. So I'm gonna say r prime of 0. Now that's a light color. Let's see if I can do pink instead. So r prime of 0 is pointing straight up. I want you to notice that r prime of 0, this little is a tangent vector. It's tangent to the curve at that point. So I'm done with step 2. Now let's move on to step 3. Let's get acceleration. So first I'll get the acceleration vector, and then I'll evaluate the acceleration vector at time t equals 0 seconds to see the constant vector associated with this point. So I'll do a of t, which is r double prime. And you're simply going to take the derivative of the velocity vector. Derivative of 2t is 2. Derivative of 1 is 0. Okay, it's a constant vector. So if you plug in 0 seconds, you're still going to get 2 and 0 because there's nowhere to substitute. So what would the vector 2, 0 look like in standard position, where it's coming out of the origin? Well, you'd locate the point 2, 0 here on the x-axis, and then you would draw a vector starting at the origin over there. But I don't want to leave it there. I want to move it so that it is sprouting out of the point it's associated with, time t equals 0 position. So we're done with the time t equals 0 analysis. So let me recap. The position at time t equals 0 is right here on the vertex of the parabola. It's right there at -4, 0. The velocity vector, which is always going to be tangent to the curve. We actually learned this last week, that the derivatives of vector valued functions are always tangent to the curve. So he's just this little unit vector pointing up, and the acceleration vector, which turned out to be a constant vector, is pointing horizontally to the right. Now, I hope you can see that at this one spot, it looks like the velocity and acceleration vectors are indeed orthogonal. Is that going to stay the case? Well, wait and find out. Let's move on. Let's do some full-blown analysis at time t equals 2 seconds now. So we're doing this whole process all over again for time t equals 2 seconds. Okay, step 1, find the position. Get where is your bug if he's moving along this parabola? Where is his position at time t equals 2 seconds? Substitute 2 seconds into the original position vector. So I get 0, 2. So what does that mean? On my curve located here at the point 0, 2, that's where the bug is at time t equals 2 seconds. He's right there. He got that far. Now what? Let's go get velocity and acceleration vectors associated with that position. So we already have the velocity vector. Good news, I don't have to take the derivative all over again. I know what my velocity vector is. It's 2t1. But what would my velocity vector be at 2 seconds? Well, substitute. T equals 2. And I get the vector 4, 1. Now, the vector 4, 1 in standard position, where it's coming out of the origin, would be, first you locate the point 4, 1, so it'd be right there. And then you draw it where the tail is at the origin. So it's that guy there, but I won't give you any credit if you just sort of leave it there. You're going to have to lift that vector up and move it, and you want to maintain its integrity, so don't change its size or its direction. You want to move it, lift it up, so move him so that he's sprouting out of this point instead of the origin. So I got to see if I can do the best I can and maintain how long he is, and it looks like he's kind of pointed a little upwards and to the right, and I'm done. So there's the velocity vector at 2 seconds. Please notice that it is indeed tangent to your curve, as it should be. Now, I put 2 primes, that should be r prime. That's a velocity. So now we need to do the acceleration. So we did step 2 here. We got the velocity vector. Now let's do step 3. Let's get the acceleration vector at this new point. So step 3, acceleration, but good news, we already know what the acceleration vector is. It's 2, 0. So if we evaluate the acceleration vector at 2 seconds, we're still going to get 2, 0. Aha. Because it happens to be a constant vector, nowhere to substitute. And remember, the vector 2, 0 is pointing to the right. It's a horizontal vector. And so if I lift it up, maintaining its integrity, it's going to be pointing that way. So that's r double prime acceleration vector at 2 seconds. And I'm done. Notice that at this point, velocity and acceleration are not orthogonal to each other. Oh, no way. That doesn't look like those two vectors are making a 90-degree angle. So I hope you can see that things change.
I have a question.
Sure.
I'm not sure if I'm gonna like word this correctly, but so you know how for the velocity it was 4-1.
For
And then you
seconds, right? Right
yeah,
here.
for the 2 seconds. Did you translate it to the point 0, 2 because since it's like a tangent line, you want it to connect like both known points?
Yeah, and you want that vector to be associated with the position that it's affiliated with.
Okay. Thank you.
Yeah. And then you can see that it is in fact tangent to the curve. Okay, we're going to do another problem that's similar to what I did last week, but sometimes repetition is good. So we're going to find a set of parametric equations for the line that's tangent to the space curve. And they're giving you a vector valued function there at the point P, and they give you some coordinates of a point. Now remember, parametric equations for a line, you need 2 ingredients. You need a point on the line. Good news, we have that already. They gave it to us. The second piece of information you need is a direction vector. They didn't give us that. Well, they gave you a vector, just, figure it out. So you have to be careful because we want to get a direction vector for the line. So this vector valued function is actually a helix that if you graphed it in 3D, and I can do that for you in a second if you like, it would kind of look like a, I don't know if you guys have seen Slinkies, maybe I'm dating myself, kind of looks like that. And then if we located the point 0.04 pi fourths, let's just say it was like, I don't know, like right there. Okay. And then if I draw a tangent line to that point, it'd be something like that. So go get the parametric equations for that line. So how do I get a direction vector? We're going to use the fact, we're doing example 11 now. We're going to use the fact that r prime is always a tangent vector to the curve. One thing about computers is if they get hot, they slow down. It's really kind of sad. These solid state drives are, I think, terrible. So we have to, this is going to be a multi-step problem. It's not as easy as it seems. You have to be careful because a lot's going on. So you can maybe do it in a different order than I'm going to do it, but as long as you kind of get all the ingredients. So what's missing for me is, even though they gave me the position of the bug, let's say, or a fly, let's say a fly was going, flying along this helix, what time is it? What is T when the bug is at position P? So I'm going to do that first. So step 1, what time is it? What is time T at the position P? And and how do you find that out? Well, what you want is you're going to actually want all of the coordinates of this point.
Set the components equal to each other?
Yeah, essentially, even though, yeah, you could think of P as being a vector, even though it isn't. So you want the 3 cos T to equal to 0 at the same time that 4 sine t has to equal 4 at the same time that 1/2 t is pi fourths. Now, if this is going to work correctly, t has to be the same for all three equations. You can't get like, 2 or 3 separate times. That would be ridiculous. So let's hope that the same value of t solves all three of these equations. Does anybody see what value of t would work for all three of these equations here? I would solve the easiest one of all. Let's just solve this one here and see if it works for the other two,
So
right?
pi over 2.
It looks like pi over 2, but will that work? Like if I go 4 sine of pi over 2, does that really equal 4? Yes or no?
Yes.
Yes.
Good deal. And then try the other one. Does 3 cos of pi over 2 really give me 0?
Yes.
Yep. Okay, we're good. Good news. We found time. It's pi half seconds. Save that for later because we're going to need it. Now, step 2 is we're going to get r prime. Okay, and the reason why we're claiming that r prime evaluated at the pi half seconds will give us the direction vector for our tangent line. And then we're going to be good to go because we'll have all the ingredients we need to get the parametric equations for that line. Yay, us. So this is a pretty easy vector valued function to differentiate because we all know how to take derivatives of cos and sine and 1/2 t. So to get r prime, we just take it component by component. Let's see, the derivative of 3 cos. I
So
think it's negative 3
it's
sine.
gonna be VT, right?
Yeah, but I can also call it r prime. They're one and the same.
Yes, yes.
Yes. And then let's see, the derivative of 4 sine t, I believe is 4 cos t. And the derivative of 1/2 t is just a half. Good news, I got my velocity vector. Yay! But now I need to evaluate it at the pi half seconds because it's going to be affiliated with that position when time t equals pi halves. So I'm just going to substitute t equals pi halves everywhere and see what constant vector I get. And that's going to be the direction vector for my line. Now, sine of pi halves, I believe, is 1. So negative 3 times
0,
1.
half.
Mhm. How about cos of pi halves?
0
Yeah.
and half.
Yeah.
As
And
for
now-
acceleration, it's gonna be 0, -4, 0.
Don't need acceleration at all.
Oh.
Doesn't come into this conversation. So you just have to worry now. So this is our direction vector for the line. And we already have a point P on the line because they gave it to us, remember? The point P was this coordinates 0, 4, and pi fourths. So my step 3 is put it all together, get the parametric equations. Because you have everything you need now for the parametric equations for your line. So you want to go x equals, y equals, z equals, and then you can put the coordinates of your point, 0, 4, pi fourths, plus, and then the direction vector has the direction numbers, negative 3t plus 0t plus a half t. Now, you know that a term 0 is kind of, you don't need to put it in there. So x can be streamlined a little bit just by saying simply x is negative 3t, and then 0 times t is just 0. So I don't need to put that in there either. Why waste time? Y is just simply 4, and z is pi fourths plus a half t. And this is your final answer for the problem. This is classic, folks. This is like a classic problem. So I wanted to see if I can use my I have some. You can oops. You can figure out, like if you watch a YouTube video, you can graph vector valued functions on GeoGebra, but it's not as easy as my software. That's why I'm just using this. Because I don't have to do as much and I'm not as well versed. So I'm just putting in the components of my position vector and see if I want to do my parameters. Okay, hang on a minute. Let me just see if I can. Oh, here we go. So I just want to change my parameters. See if I can get the whole thing. Sometimes this is a little bit grouchy when I'm trying to get everything. But it's kind of fun if it works. Okay, there's a little piece of it. It's not showing me the full thing. So it seems like it reverted back to what I didn't want it to revert to. See if I can get it to jack up a little bit. Give me some more range. Come on, baby. Show me more. There we go. Ah, that's a helix. So you can see that the curve, if you can imagine some object moving along that curve, like a fly or something like that, you can find its position, you know, locate a position and then draw a tangent line to it. And we just found parametric equations to one position on this nice little helix. So that's kind of fun, I think. Pretty cool. So let's do example 13, shall we? So this one's a little bit tricky, but I like it because it segues into what we need to complete today, which is projectile motion. So you're going to have to integrate twice. And this is similar to what you were given when you did a Calc 1 problem. So before I even do this problem at all, I want to remind you that when you took a Calc 1 class, you know, I don't know how long ago, maybe it was a long, long time ago, who knows? Do you remember being given an acceleration, you know, like say, you know, I'll just make something up. Let's say g of x is some acceleration function. I'll just make something up, you know, x squared plus 1. And they told you that was acceleration. And then they wanted you to integrate 2 more times to get the position vector. Okay, so if they gave you an acceleration, and they didn't talk about vectors, but they just talked about a function, then your velocity would be the integral of acceleration. And then you'd have a plus c, but then you would figure out the plus c given them some initial condition where they would tell you, well, the acceleration evaluated at 0 is some number like 7, you know, 7 or something. And then you can use that to get your particular solution for your velocity. And then ultimately your position function was equal to the integral of velocity. And then you'd also end up getting something plus a c. But then you'd be given some initial position. I'm just going to make something up like -2. And that would help you find the other plus c. And then you'd be done. Does anybody remember having to get particular solutions in such a way from a Calc 1 class? How about everybody hit the raise your hand button there. Let's see here. Check it. Okay. 1, 2, 3, 4, 5, 6. Okay. 7, 8. Yes. Okay. Some other folks are not remembering that. I don't know. Maybe you did or didn't. Okay. Well, all right. So about half the class did not remember doing that. Oh, that's unfortunate. And I just want to say I'm sorry to hear that. Well, maybe you can do sort of a mini review here. I'm not going to review a Calc 1 problem though. Sorry. That would be on you to go review. But we're going to do that kind of strategy in the conversation of vector value functions. So what's it going to be? They're going to give us some acceleration vector and then some initial conditions, and we have to go find the position vector. So we're going to go backwards now. So the last couple problems we had to differentiate. They gave us the position vector and we had to take a derivative to get the velocity vector, and we had to take another derivative to get the acceleration vector. So now we're going to go backwards. What if they give you the acceleration vector and they want you to get the position vector? So now we have to anti-differentiate, also known as integrate. So that's how we're going to roll. So here they're telling us that the acceleration vector, and I'm going to write this in component form, just because you know me, I prefer component form. So there's the acceleration vector, fabulous. So now what? You want to get the velocity vector. So that we'll call that v of t, or you could call it r prime, same. And we need to integrate the acceleration vector so that we can get the velocity vector, okay? So, I don't know why that won't go away. So you're going to, sorry, I'm just trying to figure out how to get rid of, weird. I was just going to stay there. Okay, so I'm going to go, all right, so I'm going to integrate 0, 1, 2 dt. So I'm going to integrate each of these separately. So as you know from last week's material, I'm really just going to integrate each component separately. Okay, so does anybody know what the integral of 0 is? Not a trick
T.
question.
Just T.
Careful. That would be the integral of 1.
Zero.
Constant.
0. It's 0 plus C1. And I want to see the plus C1 on there, not just plus C, because we're going to get 3 different constants of integration. I need you to use subscripts to make the distinction between each constant of integration. We did this last week. This is the notation. Now, the integral of 1 is, in fact, t plus C2. And the integral of 2 is 2t plus some constant of integration. We'll call it C3. Now, how do you get your C1, C2, C3? You got to be careful, folks. So what is the initial condition for velocity? You know, what did they say for the initial condition for velocity? And this is a hard word problem because they didn't give it to you outright. They didn't go, well, velocity evaluated at such and such seconds is this vector. You have to glean it from the word problem. They did give you an initial point. That is not initial velocity. This is actually the initial condition for position, believe it or not. This is telling us that once we get the position vector r, that at 0 seconds, it should be located at 1, 2, 0. So that's one of the initial conditions. What about initial velocity? Now, this is tricky, but they said rest. And what that means is that at time t equals 0, velocity was equal to the 0 vector. So it's saying that v of 0 is in fact the vector with components 0, 0, 0. Okay, so right now we have the velocity vector as a function of t. So if we evaluate the velocity vector at 0 seconds, we'll get 0 plus c1, 0 plus c2, 2 times 0 plus c3, and that needs to be 0, 0, 0. Now, if you equate each and every one of these components to each other, this one's kind of obvious. It'll turn out that C1 and C2 and C3 are all zeros. Does that always happen? No, but you have to be careful. We'll do another example later. Well, that doesn't turn out to be the case. You have to be very careful and solve for C1, C2, C3 separately. Okay, now what? So now this is what we have so far. Our velocity vector is in fact 0, comma t, comma 2t, because it turned out all the constants of integration were 0. Okay, does that happen all the time? No. Now what? Now get position. Position is traditionally called R of t. So how do we get R of t? You go R of t, the position is equal to the integral of velocity. You're going to integrate the velocity vector now. Okay, so what does that mean? Well, component by component, you will go ahead and take the integral of our velocity vector. So I'm saying that R of t is going to be the integral of this vector with respect to time. And so you know the drill. You're going to integrate separately 3 times. And the integral of 0 is 0 plus C11. I'm going to use different subscripts now because I don't want to have them get confused with the other constants of integration. Notation matters, people. Don't get sloppy. So C11, C22, C33, what are those guys? Well, they did tell us, so this is what R of t is. This is what we have so far. They did tell us that R of 0, since our initial position was 1, 2, 0, so if we evaluate R of t at time t equals 0 seconds, we'll be able to set these two equations equal to each other. So set equal, and then you'll get your C11, C22, and C33. And it turns out it is going to be 1, 2, 0. So C11 is 1, C22 is 2. Now, but see, a lot of you wrongly thought on the quiz that your initial condition gave you the C1, C2, C3. It doesn't. And so some of you kind of bombed that last problem on the quiz because you thought it was the case. So my final answer, no, almost final answer is my R of t is now going to be, after I plug in my C11, C22, and C33, it's going to be this vector here. Now, I'm not answering the question yet because the final question for this word problem here, let's go back up there. They wanted us to find the location of the object when time t was 2 seconds. You're going to go, finish out the problem. So the position at time t equals 2 seconds is R evaluated at 2. So you're going to go ahead and substitute 2 seconds into this wonderful vector valued function. And that will give you the position. So 1, 4, 4 is what I get. And that is the final answer for this problem. This is classic. Okay, you guys want to try one? Sure you do. Okay. I'm gonna have you try, let's skip example 14. Let's have you do example 15, because you can't, okay? So I want you and a buddy to try example 15. Let me start walking you through it before I throw you into the breakout rooms and you can talk to your partner. They're giving you a derivative of a vector value function. They're calling it drdt, which is, drdt, if I use notation, that's the same as r prime. It's r prime. So they're giving you a velocity vector. Okay, great. Velocity, hey, thanks. And they're giving you an initial condition of position. Your job is to solve this initial value problem and get me an R. Get me the R. Get this. That's your goal. So, I want your final answer as a function of t, R of t equals stuff, as your final answer. Okay, so you and a buddy, I'm going to throw you in some breakout rooms here. So when you're doing one of these differential equations, you're going to look at the derivative that they gave you and you'll anti-differentiate to recover the function. So we're going to basically say that R of t is equal to the integral of dr dt, which is the same as basically saying the integral of r prime. And they gave you r prime. They said it was, I'm going to put it in component form, t cubed plus 4t, and then the next component, e to the negative t, and then 2t squared. So you're going to just integrate 3 times, and this isn't too hard to integrate. So you're going to end up where your r of t is going to look like, and I'll leave a lot of room, when you integrate that polynomial, you should have gotten what, t to the 4th over 4 plus 2t squared plus some constant of integration, call it c1. When you integrate e to the negative t, a negative e to the negative t plus c2, comma, and then when you integrate 2t squared, let's see, 2/3 t cubed plus c3. So if you make it this far, you'll get some partial credit. Now what? Well, they gave you an initial condition. They told you that r evaluated at 0 seconds is the vector with components 1, 1, and 0. So we want to substitute t equals 0 into our big old r of t. And this is where you have to be kind of careful, because a lot of people go on automatic and they think, oh, I know how this is going to roll. So the first component here is basically just c1, and you want to equate these two vectors. So c1 had better equal 1. Okay, there you go. Now here we're saying that negative e to the 0 plus c2 had better equal the second component of our initial condition. But then wait a minute, isn't e to the 0 1? So negative e to the 0 is negative 1. And when I solve for c2 by adding 1 to both sides, I get my c2 is equal to 2. Aha. And then here I have 0 plus c3 had better equal 0. And then solving for c3, I get 0. So your final answer, when you write it all up, had better be a big old vector. So use brackets, or if you like the standard unit vector format, that's fine too. And you give me all of the components in turn with the correct constants of integration. Okay? And we're done. Any questions here? So now let's do projectile motion. So one of the classic applications of vector valued functions is projectile motion. And projectile motion is a very special case of motion. It isn't like everything motion. It's a special case. So a projectile is an object that gets thrown or shot or kicked or hit. And then after it leaves the person's bat or hand or whatever, gravity is the only force acting on it as it sails through the air. So here's a picture. Let's say it starts from some initial height, somebody throws the ball or whatever, and it kind of makes, an upside down parabola for the curve. So if you're given some initial velocity, and that initial velocity vector you can see is tangent to the curve, and as the object sails through the air, you can see that the acceleration vector here is always pointing down, because the acceleration has to do with gravity. It is gravity. So let's take a look at the quick derivation here. And this is a little physics lesson, because our physics folks use this. So when you have a projectile of mass m, the force due to gravity is F equals negative mgj. It's going downward vertically. And the acceleration due to gravity is one of two numbers, depending on which system you're using. If you're using the English system, it's 32 feet per second, which is sometimes written as 32 feet per second squared. On the other hand, if you're using the metric system, and I usually round to 9.8 myself, it's 9.8 meters per second squared. When you're doing a word problem, be very careful that you use the correct G, because they may not give it to you. And if you screw up the G, the whole rest of the problem goes down the toilet. So if you're given a problem where they start talking about, hitting the ball, over a 20-foot fence or something, you better know, I'm not in the metric system, and I better use the number 32. Okay, so by Newton's second law of motion, the same force that produces the acceleration has to satisfy this equation, F equals ma, and that's a classic physics equation. So what do we have? We have that this force had better be equal to that force. They're equivalent. So we're going to say ma had better be the same as negative mgj. So if I divide both sides of that equation by m, the m's cancel, and I'm left with the acceleration vector is exactly negative g, which is a constant, times j hat, okay? Or if you want to have your acceleration vector written in component form, it'll look like the vector with component 0 and negative g, same thing. So now let's do solving differential equations. So let's say you have a projectile of mass m. It's launched from an initial position. So this is at time t equals 0, r naught, that's a vector. And let's say it has an initial velocity. Initial velocity means at time t equals 0. And we want to find its position vector as a function of time. So we start with acceleration, which is basically r double prime. So that is going to be 0, negative g. Or we could just write, negative g, j hat, same thing. So what are we saying? We're saying velocity is going to be, we'll call it v of t. It is going to be the integral of a of t, dt. And so when we integrate negative g, j hat, dt, we're going to get negative g times t, j hat, plus some constant vector. I'll just call it c1 with a little arrow. But we're going to use the initial condition for velocity to solve for the c1. And they're telling us that, velocity evaluated at 0 seconds is going to be this initial velocity vector v naught. So when you plug in t equals 0 here, you're basically going to get that c1 is v naught. They're the same guy. So what do we have so far? What we have is our velocity vector is going to look like this. Negative gt j hat plus the initial velocity vector. Fine. Now what? Now you need to go get position. So the position vector, which we'll call r of t, that's just classic notation. Yeah. It's really slow. We want to integrate the velocity vector, and that'll give us position. Okay. Now, what about the what about that? So r of t is going to be the integral of negative gt j hat plus this initial velocity, we're calling it v naught, and integrate with respect to time. So we're going to get negative a half gt squared j hat plus this constant vector v naught times t plus some constant of integration, we'll call it c2, but using the initial conditions where the initial position is r naught, and using the same idea of plugging in t equals 0, this c2 is essentially going to be the initial position, r naught. And we're pretty much done, except a little bit extra. R naught is typically the height, the initial position. It's right here. This height here is h. So what they basically say is 0h are the components of r naught. Okay, and since speed is equal to the absolute the magnitude, if you will, of v naught, let's just say that it's some scalar v naught. And let's say that the angle that the vector makes with, and I'm talking about the initial velocity vector here, v naught. Let's say it makes some angle with the horizontal of theta. You can break down your v naught to look like whatever the magnitude of it is, that'd be speed, V naught cos theta, comma, V naught sine theta. So that's typical for your V naught look. So these are your two initial conditions kind of broken down into their I and J components, if you will. So when you put it all together, what is your initial, or what is your vector valued function for position going to look like? So they're talking about this angle of elevation. You got initial height of h, initial speed of v naught. Here it is, fill in the blank. RT equals, and then if I put this into component form, because that's usually the way I like to roll, like so. And so the first component is the speed, v naught, cos theta. That's just some number, you know, when you figure it all out, times t, comma, height, that's initial height, plus v naught sine theta times t, and then minus 1/2 gt squared. So these are the two components, and we're going to only look at projectile motion in the plane. You can talk about it in 3D, and I'm going to skip it. Your book goes over it a little bit. I don't put any homework or quiz problems to do with 3D projectile motion, so don't even worry about it. Let's just worry about 2D. Okay, if you can do 2D, I'll be happy. And G is the acceleration due to gravity. I do want to say, when you work these problems on a quiz or an exam, for me, if you just use your physics textbook formulas and not this projectile position vector, I will take away all your points. Some of you did that on last week's quiz when I had that force diagram of the minivan. Some of you just whipped out your physics stuff and got the right answers, and I took away all your points. That's going to happen again for projectile motion. I want you to use the ideas here in Calc 3, which is vectors and vector valued functions. Not just, oh, well, you know, mg sine theta or whatever my physics prof told me. Let's do one example and then we'll call it a day. Okay, so using this position vector for a projectile and knowing that when you graph this, it's always going to have this look to it. Every time you graph it, it's going to be an upside down parabola, just like this. Okay, that's what it looks like every time. Every time. So using that knowledge, let's have our projectile be a baseball. And let's say it's hit 3 feet above ground. Folks, there's your H. Boom, they just gave it to you. Boom, 3 feet. 100 feet per second, that's your speed. That is your V naught. Add an angle of 45 degrees with respect to the ground. That's your theta. So they gave you your H, which we need when we stick it into this position vector. They gave us the speed because it uses the V naught a couple times. And since we have a cos theta and a sine theta, thankfully they gave me the theta for my cos theta and sine theta. Now what they didn't give me is my G. You have to figure out which G to use. Which G should it be obvious that I need to use given some of these basic pieces of information?
Mars.
I'll give you a hint. You have two numbers to choose from. Is it 32 feet per second squared, or is it 9.8 meters per second squared?
32 feet per second.
Yeah,
Metric
is-
is superior 9.
Second squared. Please say per second squared.
Does that mean you have to convert?
There's no
Or-
conversions that need to be done. You will simply use 32. We're not going to convert this whole problem to metric. Stay in the world of English system for this entire
Oh,
problem.
that's atrocious.
Well, everybody's entitled to their opinion. So look at all the parts we have to do before I can let you free. Oh man, really? Yeah. Let's go over these in turn. This is going to be on a future quiz. This material again is not going to be on your midterm, so don't worry. It will be on a quiz. Okay, so we want to find the maximum height of the ball. We want to figure out if it's going to clear a 10-foot high fence that's located 300 feet away from home plate. Oh my goodness. We want to figure out how long it takes for the ball to hit the ground. And what's the range? You know, how far away from home plate when it finally hits the ground is it? Those are the 4 things they want. And we're going to start with the position vector. So let's first put that together before we do anything. And then from there, we're going to glean the rest. So R of t for us is going to be a vector. So write it down. You want full credit. Let me just put my little brackets here. Oh boy, that's my fun erase tool. So if you look at the theorem, you're going to have 100 cos 45 degrees. That's going to be some number, whatever that number is, times t, comma. The height, the initial height was 3 feet, so 3 plus, then you're going to have the 100 sine 45 degrees, whatever that number is, times t, minus 1/2 g, and we all agreed that g was 32 feet per second squared for this problem, t squared. Okay, so we start there. Now I'm going to clean this up just a little bit because I can. Cos of 45 is square root of 2 over 2. Sine of 45 is also square root of 2 over 2. So I'm going to do some reducing there because 100 divided by 2 is 50. So 50 square root of 2 times t is the first component of this position vector. 3 plus 50 square root of 2 t minus 16t squared is the second component. Okay, now maximum height. This is a 2-part problem, so this is going to take some time. If I look at the picture of the projectile motion, the place where it reaches maximum height is at the vertex, if you will, of this parabola. Yeah. So that's as high as the ball gets. So my max height is going to be, you know, what's the vertical height there? Does everybody see it's a vertical height? So how the heck do I get that? Now it turns out what we're going to do is we're going to first look at the velocity vector because that's going to help us get max height. Really? Yeah, because remember velocity is always tangent to the curve. So right at the highest height, the tangent vector happens to be a horizontal vector because there's no vertical component. It doesn't mean the ball stops. The ball doesn't stop when it reaches the height. It's still moving forward. It doesn't have a vertical component though. The vertical component of velocity at this moment, and you can write this down because this will help you do one of these problems. The vertical component of velocity is 0 at the moment it reaches the maximum height. So the way you're going to do this problem is 2 parts. You're first going to find the velocity vector, r prime, and then you're going to force the vertical component of this velocity vector, you're going to force it to be equal to 0 and solve for time. And that'll give you how long it took for the ball to reach maximum height, time t, and you'll substitute that time t into the vertical component of position to get the actual max height. It's so exciting. Here we go. So the velocity vector is going to be pretty easy to get. Just take the derivative of the components of position. So I get 50 square root of t, and then I get 50 square root of 2, 50 square root of 2, minus 32t. Boom, there's the velocity vector. Now what? You want to force this vertical component to equal 0. So set equal to 0 and solve for t. So you're going 50 square root of 2 minus 32t has to be equal to 0. That has to be true, okay? So then what? Well, how about if you add 32t to both sides? All right, that's easy enough. How about dividing both sides by 32? Okay, and then you may want to whip out your calculator to approximate because t is exactly 50 square root of 2 over 32, and that's approximately 2.21 seconds. Now, that's not the answer, okay, because they wanted maximum height. But you're going to substitute this into the position vector, r, his y component. So I'll do like a subscript y. What do you mean? Well, the y component is that big old honking thing there. So if you substitute 2.21 seconds in place of the time t, and then whip out a calculator, of course, because I don't want to do any of this arithmetic in my head. Oh dear. And I'm going to just round it to the nearest whole foot. I get approximately 81 feet. And that's the answer to part A. So the ball reaches a maximum height of approximately 81 feet. That's pretty high up there. Cool. So now the parts B and C, how do we even think about this? Well, you want to think about what your position function is doing. So if you look at the picture, 300 feet away from home plate, there's this fence they got there. It's 10 feet high. Is this ball going to hit the fence, or is it going to be able to sail over the fence? Because if it sails over the fence, the guy for sure is going to get that home run. And yeah, home free. Otherwise, maybe not. So what you're going to do is you're basically saying with this 300 feet away, you're saying the x component of position, Rx, is equal to 300. Okay. So and then the Ry would be the height. So we need to find what time it is or how long it takes for the ball to make it where the range is 300 feet, and then we'll plug that in and see if that's going to give us a vertical component that's bigger than 10 feet or not. Oh, well, how do we do that? So here's what we want. We want Rx to be 300. Okay, so if you look at the position function, not the velocity, the original position function, and you look at his x component, you're basically saying you want 50 square root of 2 times time t to be 300 feet. Okay, and so you're going to solve for time by dividing both sides by 50 square root of 2. Okay, and so the exact time is 300 over 50 square root of 2. But if I plug that into my calculator, I get approximately 4.24 seconds. That's how long it takes for the ball to make it 300 feet away from home plate. That's not the answer. So what you're going to do is your Ry is your vertical height. So you're going to look at substitute time t equals 4.24 seconds into your vertical component of your position function, which is this big old sum right here or right here, same thing. So you're going to do some substituting. You're going to go, okay, what's 3 plus 50 square root of 2 times this 4.24 seconds minus 16 times t squared, 4.24 getting squared. Ooh, yucky. Get out the calculator. I get approximately 15 feet. So now this is a yes or no question. If the vertical height of the ball is 15 feet when it's 300 feet away from home plate, will it clear that 10-foot high fence or not?
Yes.
Yes, it will.
Yep. Yay. Yes, it will. And the guy gets to go running the home. Yay, home free. Fantastic. So letter C and D are kind of connected because once we do one, we can quickly finish out the other. So here we go. How long does it take for the ball to hit the ground? So once it leaves the bat, how many seconds you have to wait till it hits the ground? So if you look at our picture here, this upside down parabola, it's going to finally hit the ground. Don't say velocity is 0 when it hits the ground, because that's not true. It's traveling pretty fast when it hits the ground. What is true when it hits the ground is your vertical component, your Ry, is 0. So your vertical height is 0. So what you can do is you can set the vertical component of position equal to 0. Now this is kind of a bummer. Why is it a bummer? Well, it just is, because this is a quadratic equation. And when you took algebra, you solved quadratic equations a whole bunch of times, right? So you're experts. Can you say quadratic formula? I want to see this in action. T equals negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is the lead coefficient, which is negative 16. B is equal to 50 square root of 2. That's a weird number. And C is just 3. So when you substitute all of those values in here, negative 50 square root of 2 plus or minus square root of 50 square root of 2 getting squared minus 4 times negative 16 times 3 all over 2a, 2 times negative 16. Yuck. Now, when I punch this up, remember, because of the plus or minus, you're going to get two solutions. One of the solutions I get is approximately a negative 0.0013 seconds, which is impossible unless you can go backwards in time. So we're going to discard that solution. The other solution is approximately 4.46 seconds, and that's the one we're going to go for. So there's your answer for part C. It takes about 4.46 seconds to hit the ground. Now we're going to look at letter D. We're going to use our answer to letter C, 4.46 seconds, to figure out what the range is. So what do they mean by the range? Well, how far away from home plate? It's pretty far when the ball finally hits the ground. That's what they mean by range. So you're going to want to know what Rx is at the time, at the point when time t is 4.46 seconds. So easy peasy to find, because you're just going to substitute 4.46 seconds into the t for the horizontal component of the projectile motion vector valued function. So you're going to go 50 square root of 2 times t, which is approximately 4.46 seconds. And then use your nice calculator, and I get roughly 315.5 feet, because we're using the English system. So that's how far away from home plate that ball is going to be when it finally hits the ground.